Okay, hey everyone, I'm Arjun. I'm a second year grad student at USU, working on Scott County. I want to tell all of you about some of the work we've been doing on the detectability of circumbinary planets in Rome. So circumbinary planets are planets that orbit a binary star system, and they're broadly classified into two types. S-type circumbinary planets orbit one star in a wide binary system, and P-type circumbinary planets orbit both stars in a relatively close to the binary system. And I'm mostly concerned with the latter type. We know very few circumbinary planets today, and the large majority of those have been discovered by Kepler through transits of eclipsing binaries. We have discovered a few microlensing circumbinary planets, and these usually have wider orbits. And most of these light curves, most of these systems are light curves that cannot be fit by a two-lens one-source model. They usually have extra features for which you need to add a third body to completely to fit the light curve well. And this is an example of one such light curve. So here you have two peaks due to the binary star system and additional perturbation with the planet. So the question I'm trying to answer is, can we expect to find many more circumbinary planets in Roman? And in what regions of parameter space are circumbinary planets most detectable? So I think a lot about caustics of circumbinary planets, so I'm going to subject all of you to that torture as well. A small note in terminology, I'll be using the word binary caustic, binary light curve, or binary. So I'm using the word binary caustic light curve trajectory to refer to the binary star system. I'll be using planetary light curve model to refer to the system, the planet around a single star with the combined mass of the two binary stars. Both of these are binary length systems, but to refer to a general binary length system, I'll try to say two length one source. So, to a first approximation, circumbinary caustics are a superposition of caustics due to the binary star system, as well as caustics due to the planet around a single host star. And if you have a trajectory that passes close to both these caustics, then we can see features due to the binary star as well as the planet in the light curve of the circumbinary planet, and this would make this system easily detectable. So on the left panel, you can see resonant planet caustic superposed on a binary central asteroid caustic, and this superposition is also creating certain intersections within the caustic. This usually happens when the size of the planetary caustic is comparable to the size of the binary caustic. When the planet is closer to the binary star, the planet doesn't perturb the central caustic as much, but it produces two additional planetary caustics. And so I forgot to mention, in green, in the background, I've plotted what the planet caustic would look like without the binary star. So you see that it's not a perfect superposition, it's slightly displaced from where the planet caustic would have been. So in the close configuration of the planet doesn't perturb the central caustic as much, but it produces two additional planetary caustics. And again, in green are the caustics of the planet without, if the star system was a single star instead of binary. And you see that the circumbinary planetary caustics are slightly displaced compared to where the caustics would have been without the binary star. I'll get back to this later. In the white configuration, again, the planet produces, you can see both the white planetary caustic as well as the central binary caustic. So we simulated hundreds of light curves with different trajectories for each circumbinary system in order to figure out which circumbinary systems are detectable. And for each light curve, we first fit a point length model. And if a point length model doesn't fit the light curve well, then I fit two length one source models, one starting from the initial condition of just the binary star itself, and the other starting from the initial condition of a planet around a single star. And if both these two length one source models don't fit well, then we say that we have detected a circumbinary. We also check that these two length one source models can actually fit light curves produced by just the binary star or just the planet to make sure that our algorithm is working well. So I did this for a number of different planets with different mass ratios and separations. And for each planet, I sampled trajectories over all the interesting regions of the cosmic plane. So for resonant caustics, all the trajectories within that green shaded regions were detected. Basically, if a trajectory gets close enough to the resonant caustic, you can see features due to both the planet and the binary, which makes them easily detectable. When the planet is in a closed configuration, it again produces two planetary caustics. And in this case, for a Jupiter mass planet, the planet is massive. It also perturbs the binary central caustic. So you can see that there's the central asteroid has some additional features. So I've plotted all the trajectories where we could say that the system is a circumbinary in green. In order to plot all the trajectories where we could detect either just the binary feature or the planetary feature, and red have plotted trajectories where we couldn't see any deviation from point lengths. You can see that for a large region around the central caustic, we're able to tell that this is a circumbinary, and this is because of the perturbation of the central caustic by the planet. We're also able to identify the circumbinary nature of this system for trajectories that go through both the planetary caustic as well as the binary central caustic. And overall, we found that the circumbinary nature of the system was detectable in about 60% fall light curves, which show some deviation from a point length. When I replace this Jupiter mass planet with an Earth mass planet, you see that the caustics are much smaller, and the Earth mass planet does not perturb the central caustic. So obviously, we detect much fewer trajectories. We're able to, so on the left, I've shown a light curve for a trajectory that goes through both the planetary caustic as well as the central binary. So you can see this feature due to the perturbation by the planet, and the binary also modifies the peak. So the presence of both these features is an unambiguous signature of the circumbinary. Aside from just trajectories that pass through both the central binary caustic as well as the planetary caustic, we're also detecting a few trajectories that go through just the planetary caustic and don't go anywhere close to the central binary. So we're not 100% confident of this result, but this could be because planetary caustics in circumbinary systems, as I mentioned before, are displaced relative to where they would have been if the central host star was a single star instead of a binary. And this along with being displaced, these caustics also have slightly different size. So a combination of these factors could be allowing us to detect some trajectories that go through just the planetary caustic without any perturbation without passing close to the binary central caustic. And if this is true, then this will help us detect many more circumbinary planets. Here's an example of a planet in a wide configuration. So we're detecting a large number of trajectories close to the central caustic. As you can see, there's a big green region. And this might be because the planet in this case is slightly perturbing the binary central caustic. So the black, I've plotted what the circumbinary caustic looks like, and in blue, the caustic for just a binary star system without the planet. So the planet is slightly changing the shape of the central caustic, and this might be allowing, and this is probably allowing us to detect a large number of trajectories close to this central caustic. We're also detecting a few trajectories that cross just the planet caustic without interacting with the binary caustic. And this again is probably because the planetary caustic in a circumbinary is slightly displaced and has a slightly different shape compared to when the star is not a binary. Along with that, we're obviously detecting trajectories that pass through both or close to both the planetary caustic as well as the binary caustic. We can also detect the presence of a binary host star even when the binary does not cause any perturbations in the light curve. So if you can measure microlensing parallax and you can measure one of either finite source effects or lens source proper motion, we can determine the mass of the lens. Further, for this system, if you also measure the flux of the lens, we can use the mass luminosity relation to check if the source is a binary. So since the mass luminosity relation is not linear, the flux produced by two stars won't be the same as the flux produced by one star with the same mass of the two stars. And I'm planning to include this in my simulations to predict the use of circumbinaries as well. So there's a lot of work left to do. The circumbinary parameter space is complex, and these simulations are really time intensive. I was supposed to include a plot of detectability for regretted Planck parameters, but that got into a lot of computational issues. But I also intend to explore the effect of changing the binary star parameters. And the eventual goal is to include circumbinaries in a full simulation of Roman to predict the expected yield of circumbinary planets. So stay tuned for more results. I'll leave my summary slide up, and I'm happy to take any questions, comments, or suggestions.
Yeah, so in taking signals from the second star, have you done anything to confirm that they're not also modeled by some other model, like other planet? So in two cases where we have signals near the peak of a planetary microlensing event, there's another signal that could either be another star or another planet. And then also, I should say that in the case of 349, one by microlensing, that planetary signal, that signal can be explained either by a planet or a star, and it's just the parallax and flux measurement that, and so for that event, if it would have been lower magnification, we wouldn't have seen that signal. We still would have almost the same confidence that it's a circumbinary planet.
Right. I've not explored any degeneracies, and certainly have not explored looking at whether this could be fit by other triple lens models. But I expect, at least, so I'm just looking at closed binaries for now. And I have to think about this, but I'm not sure if, like, a planet is very much smaller in mass. So I'm not sure if that another planet could mimic the signal of a closed central binary star. But yeah, I'll have to think about this. And doing circumbinary simulations is hard enough, so we didn't want to complicate this by for other geometries.
Did you have blending in your simulations?
No. These weren't simulations of stars of like fields themselves. These were just simulations of light curves for certain parameters. I haven't done like a full simulation.
No blending.
No, I think I set the blending to 0. Yeah.
Yeah, correlated to this is that if the signal on the planet is detectable only because the caustic is displaced, actually this could also be made by a trajectory with the parallax. In that case, you would intercept the planet in a different position. Probably there would be degeneracy in that case, and then you could recover it with a simple simple star plus planet with some parallax.
Yeah, that's possible. Yeah.
Or bit of motion.